Is anybody here afraid of the dark? Is this gonna work? All right. Hey everybody, how's it going? I'm Dave Gullo. Actually, before I get started, how many people here have seen the Wackoon demo that Daniel gave last time? All right, pretty good amount. All right, so I was kind of joking with him earlier, like, where'd you hide it? Like, where is it? Because, like, you know, if you guys are starting to fall asleep, he's gonna hit a button and squirt me with that thing. So, all right. So tonight, I'm really happy to talk about our use of Scala and node.js in our stack. A couple ground rules I want to get out first before I get going. I'd like to make this interactive, and it's a little dark in here, but our eyes will adjust and stuff. So, you know, along the way, if you want to pause and ask me a question or just shout it out if I can't see you, like, let's totally do that. I'd like to, you know, keep it open. The one thing I ask is if we kind of start to rabbit hole, I do have a lot of slides and a lot of content to cover, so I may just put it on the virtual parking lot, and then we can kind of go offline afterwards and have a little more discussion if it comes to that. It's not. Let me give you a quick little bit about VideoAmp real quick. We are actually, our purpose is to reinvent the media ecosystem through innovative technologies. So we love solving complex problems with innovative and elegant solutions. Our technologies enrich the dynamics between content owners and advertisers, and this leads to increased programming investment, higher quality content, and a symbiosis that benefits the media ecosystem. And that's advertisers, content owners, and viewers, right? Our mission is to enable advertisers and content owners to transact seamlessly across all screens. So we're building the world's first total video platform to enable advertisers and media owners to transact across all these different devices. And that could be basically these kind of things. Make sure I'm on the same page. All right. So whether it's a TV or your desktop or a tablet, OTT meaning like gaming consoles, Apple TVs, Roku's, Fire Sticks, all that kind of stuff. What we do is we put video advertisements on all these devices. And we do some interesting things to connect them and make it a cohesive experience. So before we get super deep in the stack, let's just have a few little grabs of our product. They'll give you some intuition. And actually, we have the man responsible right here in the front left corner. He's actually the lead front-end engineer that did this project. So let's say, hey, David. All right, so just a few quick slides of our product experience. I just want to get it out in front. Like basically, well, that's just a login. That's nothing. But you know, we basically have lots of stats, lots of charts, lots of D3, I believe. Right? Is that D3? Yeah. Lots of different stuff about targeting and essentially giving you a sense of where, when, and how that these video advertising campaigns are going to run. And actually, this is a fun view. We actually show our customers why they're losing, or maybe they're not filling a campaign good, or as good as they could. And so, you know, here's another view there. And this is kind of a fun one. This is kind of like the Fruit Stripe bubblegum screen. This kind of gives you a sense of like when you're creating a campaign, you can actually target all these different kinds of outlets or devices, I should say. So this is a major part of what we're doing. It's not just advertisement for one medium, it's as many as there are. And yeah, I mean, here's just another look at those kind of devices, actually. Yeah, there are some interesting use cases of what we are doing. So we'll get a little bit deeper into the tech behind this stuff, but audience indexing, taking stuff that people do on digital devices and making it work better on television and vice versa. It's like basically indexing between the old and the new of how video is consumed. And with some of this tech, we're able to sort of sequence ads too. So let's say that you see an ad on one device, we can have you seeing the next version of that on the second device. I think a good example of that would be like Super Bowl ads. There's always like the Doritos ad, right? And they're like, see what happens next. And then you see ad number 2 on a phone or some other device, even though you might have seen ad number 1 on TV first. And along those lines is an interesting concept of which is competitive conquesting. So it's like if you saw the NBA Finals, we'll get into how we know that you did. We'll show you, if you saw the NBA Finals, we saw that you saw the Gillette ad, because Gillette did a big campaign, let's say. And our client, Dollar Shave Club, might want to hit you and counter that message. These guys are competitors, so they want to conquest each other's brands, basically. And that's a big part of it. You could probably think of that happening in political. It's just that this year there wasn't quite the political spend that people expected. But usually every 4 years for the presidential election, competitive conquesting is kind of a big deal. And then actually with all this data, we get into knowing when, where, and how to reach people. And that's like genres and day parting and so forth. Cool. So this is kind of a theme we'll get back to tonight over and over again. We have huge scale, but we're a pretty small company. And we're about 2.5 years old, but we've scaled up to the entire United States all at once. And it'll be fun to get into the details of that in a bit here. So at the core of what we do is real-time bidding, basically. So what happens is, and most people don't realize this, but when you see an ad on your computer, whether it's a video ad or a display ad, that's almost always auctioned, actually. And that auction happens really fast. And the time it takes for the web page to load, it will actually be happening in milliseconds or hundreds of milliseconds, and really end-to-end in like a second. And some experiences really suck and might take a page a long time to load, and it's blocking, and some really poor sites will actually block for a while they're waiting for the ads to load. But that's more of a thing in the past. A lot of really important publisher sites, they don't block like that anymore. But so what we do though is we have a seat on ad exchanges. So there's like 3 parties involved. You have the publisher over here, and that's where you go to look at stuff. And then you have an exchange in the middle, kind of like a stock exchange. And then you have all the advertisers over here, or the demand side. So the publishers are the supply, we represent the demand. In the middle is an exchange, because it's kind of akin to like buying stock straight from Apple. You don't buy stock from Apple, you buy it from a stock exchange. An exchange sits in the middle and sort of brokers all these ad opportunities. And it turns out it's quite expensive to back channel all this. Like it's tens and hundreds of megabits of traffic going basically out of band across the web to people like us. And so there's limited seats, basically, is what I'm trying to say. So there's only so many people that are allowed to sit on these exchanges and buy. And you have to spend lots of money to keep your seat. So we're on about 10 right now. And what they do is they send us bid requests. This represents, like I said earlier, all of the advertising opportunities in the whole US. And we're moving into Europe and stuff, so that too, but the market there is a lot smaller than it is in the US. And so on behalf of our clients, we're bidding, and we try to do the best to spend their money in exchange for ad impressions. Turns out, advertisers, there's quite a bit of segmentation in the space, and so ad agencies and advertisers, they don't know how to do this stuff. It's pretty high tech, and it's very expensive. The technology is expensive, and actually, so are the mistakes. So in the early days for us, some of the bugs go horribly wrong. Because remember, you're writing software that spends money all the time. So any bugs can cost you lots of money. And in fact, on average, most of our bugs cost about 10 grand a piece. And you're spending that in 3 minutes or 5 minutes. You're like, oh shit, stop the, we literally had a kill switch button. And then we made it into like a little Cordova app or whatever, where we could go on our phone and just stop the presses early on when our platform didn't have all the right checks and balances in place. We don't have to have that anymore. But so there is a lot of tech to spending money automatically, and that's pretty much what we do. When we talk about it tonight, we'll get into that stuff a little more and talk about where we're using Scala for that and node.js. So let's get deeper into it. So let's actually talk about some of the stats first. And if you read the meetup description, some of this was in there. But in fact, since we announced this meetup, we even onboarded a lot more traffic. So now we're up to 300,000 requests per second. That just went up a lot in the last couple weeks. And that's kind of a big deal for us. So we have to answer in 30 milliseconds too. So if that weren't the case, there'd probably be a lot of other architectures that might do this fairly well. But that alone costs us a lot in terms of our engineering time and optimization and our patterns of thinking and just kind of what we have to do every time we want to add one new thing to the mix, and how important it is to actually throw engineering time at it versus servers. And at any given time, that's representing thousands of active campaigns for our customers. I don't know, we may even have broke the 5-digit mark there by now, I'm not sure. So actually, let me pause there and explain what's happening in this 30 millisecond time frame. So 300,000 requests per second, that's about 20 billion auctions a day. And actually what it is it's a JSON post. So if you've ever seen JSON, it's a post that we receive, we unpack it and look at it, and inside of that there's things like the user agent and a UID that the exchange gives us, and we can unpack that and figure out a lot of things with user data on that. We can figure out what kind of targeting segments they belong to. So in that time frame of 30 milliseconds, we have to look them up in a billion key user data store, and then assess which segments that they're in. And then we need to match that to our internal demand. If we have thousands of campaigns, we have to kind of figure out, like, all right, who should this opportunity go to? Who's falling behind on their pace? Who wants to pay more for it? And who's the most likely one to win it? So we have to kind of pre-bake all this stuff really quickly and put it into in-memory data structures in order to react pretty much instantaneously. So that's the task at hand. This is a very high performance and highly tuned environment, basically. All right, cool. Trivia time. Who can tell me where this is? Somebody's had to have been there. All right, yeah. Can anybody tell me when this is? I'll give you a hint. The photo has a rounded corner. All right. Well, anybody? Yeah, so this is the spill gates at Hoover Dam. This is the Arizona side. And I was looking for some kind of photo where shit was spilling over, basically. Right? And this was it, right? And it turns out, I'm like, oh yeah. And it turns out I was there. This is in 1983. And this is one of the few times ever where Lake Mead actually was going off so much, it overwhelmed the floodgates, for which they normally control the flow. There's an attenuation on the arms, and they go back and forth, and they can sort of control how much water they spill off the dam. And if you've been there in the last 10 years, it's like 50 feet below that or more or whatever. The dam's really low compared to this. But this is a key concept with like high volume systems in that you really have to design around what the delivery semantics are. So for us, that means a lot. So the deal is, like, with guaranteed delivery semantics, like Facebook Messenger or whatever, or Whisper, or these chat programs, what you're doing is you're delivering a message to a bunch of people, and it's got to fan out, and it's got to get there, and it's got to get there fast, and it can never be dropped. It's like picking up the phone and hearing the signal, and being able to get a dial tone. Like, guaranteed delivery semantics screw up everything at low latency and high scale, and they cost you really a lot more in engineering. Luckily, we don't have that, so we get to let stuff just fall on the floor. When we're busy, we're already attending to all the traffic we are provisioned for at any given time, and that's with auto-scaling and auto-healing. But there's a top-level line we ever want to see in terms of traffic. So anything else, it just falls on the floor. And by not having to do these guaranteed delivery semantics all the way through our platform, we're able to sort of just be like, no, we're just not going to put any more machines up right now. We don't need to. We're already at the scale we need to be. And that's something we exploit everywhere we possibly can, even into like using spot market and cheap instances and extra compute or wherever we can get it from. And in fact, I've seen statistics where it can cost a company like 10x more in costs, both in terms of infrastructure, complexity of engineering, processes, all of that. So guaranteed delivery at high scale, low latency, it's expensive, and it's way more complex. So there we go. And so basically, yeah, missed opportunity from our perspective is like, well, we were too busy, and somebody else would won that auction. We don't care about that. Upstream, they do, but that's a different kind of company. That's the exchange. Right. Actually, any questions, comments so far? Yes?
With your deliveries, do you use UDP to send out the messages? What kind of protocol?
No, because it is TCP, so it's a post. The question was, what was the protocol? Is it UDP? No, it's over TCP. It's a JSON post, basically. Yeah. Okie doke. All right. Well, let's dive into the stack. A lot of different stacks I'm going to talk about, but a lot of it's going to be the Scala stuff first, and then I'll get into the node stuff, and then we'll compare and contrast, and we'll ask a lot of questions along the way and so forth. So when we first started building this, there was a lot of different choices to be made. We had good advisors, people who had been to the mountain before, and they were basically, they were explaining to us some of the technologies that we should consider and that we could use for this. And really, actually, Erlang and native C, they actually are among the best choices to do this stuff. The problem is the talent for Erlang programmers is really, 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 really tough to get. We were going to the LA Erlang meetups, and they're at a few companies, and there's like 10 people there, and then one night there's 4 people there, etc. So we literally used to joke that we'd have to hang out in front of certain companies and just kidnap their engineers if we wanted to do Erlang. And then also their leadership, their technical leadership was pros at it, super experienced. But Erlang's great in that, I don't know, how many people are familiar with Erlang here? Yeah. All right, couple. So I mean, it was used for like telco switches and really high availability stuff. And I don't remember how long ago they wrote it, but it's a very mature language, and some of the benefits are out of order, pretty much. Being able to hot swap running code. So if you have a telco switch, and going back to that analogy of picking up the phone and it's always on, these are the kinds of systems at the switching level where you're always going to get a circuit no matter what. And they're built for handling failures in a very interesting way. So with Erlang, it's an actor pattern, and we'll get into that with Scala and Akka, basically. Akka is also an actor pattern. The idea is it's a very low degree of isolation, or it's a high degree of isolation. No shared state. You're using message passing to talk between these things, and you just die really quickly. There's no real exception handling. You die if there's an exception, and you're spawned again by a supervisor process. And so Erlang, I don't think, was necessarily the very first to do this exact pattern, but they've done it pretty much the best. And some of the exchanges we work with and some of the other companies out there, they do use this. And it is a very fantastic framework and virtual machine, VM and so forth to look at. But there's just not enough talent. So we already are deeply focused with Apache Spark at our company, and that's all written in Scala too. And in fact, if you're going to do Spark, you're going to write it in Scala for best effects. So for us, Akka was really the next best thing to kidnapping Erlang engineers, right? And yeah, I mean, C, we know some of our cousin companies and stuff, they use C at the exchange, at exchange level, and they do squeeze a lot more performance out. And when you're in the hundreds and thousands of machines, like, you're actually going to get quite a bit of yield out of building things in C or C++. Oh, yeah. And I guess what's kind of neat about this Akka framework is that we get a whole bunch of stuff for free. It's all baked in. And so I was talking to our lead engineers for our bidder project, and they were chuckling about how few lines of code there really was in this whole thing, given what we get for features, right? So let's dive a little further into it. So what's cool about Akka, like with Erlang, like I was saying earlier, is it uses an actor pattern that uses these supervision trees. So the concept is, if you're way down here in task world and you're doing something, if there's some kind of weird exception that's, I don't know why, like a deadlock or just something weird, you just die, and then your parent restarts you, and then basically you're going to basically finish the work that was going to be done. Every actor has a really high degree of isolation, and they're lightweight. And they die and respawn. Okay, I keep saying that. Basically, this is really key though, because that's very lightweight when you do this, and allows you to have concurrent workflows, which we'll talk about in a bit. So you can spread out this execution. You can fan it out across cores and machines and racks and even data centers, which is this. Yeah. Yeah. So a little deeper into that, we use Akka clustering. So Akka clustering treats hundreds of machines like as if they're one big cohesive application. So while we're fielding all of this request data, it's as if it's just one service that's handling it. But really it's spreading out, and there's like services in the middle or actors that are routing and doing conditional stuff. And in fact, we actually do consistent hashing on the user ID. So like I said earlier, we have like 1 billion user IDs in our store. So what we'll do is we'll make a consistent hashing algorithm that takes that UID of all billion and spreads it. And so as it's making its way through this fabric of routers and actors along the way, we can guarantee cache locality of a user. A lot of other companies do this kind of stuff. Facebook, others, like this is definitely not novel for just us. But by doing that, we're able to get the request to wind up on the actor which should be dealing with it at that point in time, relevant user for that big request. And so by the time it gets there, you can really streamline the memory required and the actual data that's there by the time you get to this endpoint. So quick look at the front-end workflow. There's multiple layers in here. So when I say front-end and back-end, it's not like the user interface. It's actually just layers in this system that's built to answer the bid request really quickly. So we fan it out, and the request arrives at our edge as a JSON post. It reaches any number of front-end workers. It doesn't matter which one. It's kind of like a traffic cop, and it goes, here's the UID for that, and we'll start hashing a route out of that. They can coordinate the routing and then hand it off to a back-end worker. Over there in back-end worker land, it's kind of, I don't know if that slide came out. Those guys are miners. That's not my best one. So they receive the JSON bid request. And this is like now part of the 30 milliseconds timer that's going. And with the supervision tree we looked at earlier, the supervisor can be like, you're going too slow. And then it's done. And that request fell on the floor. It spilled over the dam. Water under the bridge. We don't really care, actually. So when we do timeout, it may be like, the 95th percentile is all good, but some stuff just does take too long, especially being in Amazon. There is network partitioning and like random stuff. You can have noisy neighbors, all of that. Just some stuff just doesn't fully complete. And this goes back to the non-guaranteed delivery semantics. We can let that just happen. And we're like, yeah, whatever. We'll pick it up in the next millisecond or two in terms of opportunity. So in that 30 milliseconds, we send that data down to Kafka, and that's a big, gigantic, massive buffer where we have like 2 or 3 days of capacity where we can write these billions of web requests or bid requests per day. And I'll talk about how Kafka goes into our data warehouse a little later. But that's a really quick operation. It's very, 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 very quick. It's literally just a quick write. And I think that is UDP. I don't know if we have it configured that way. And then we call out to Cassandra and some third-party vendor sources for like fraud detection. So we have to kind of look at the signature of the whole thing. And there's companies whose whole purpose is to look at that bid request and go, no, you shouldn't buy that. It's garbage. Because video has the highest CPMs out there in all of the industry. So it's where the most fraud is too, it turns out. It's where a lot of bad actors are putting fake requests of fake users on fake websites with, the rabbit hole goes deep on that. And then basically we have anything else as in-memory cache as much as we can. And then we determine the right campaign and the right price to return, kind of like we talked about a little earlier. So got to do that in 30 milliseconds. Every new operation is carefully assessed for cost versus function. So if we want to just add a new feature, we can't, like, without really testing it and putting it in the wild. And a little earlier when we were looking at that routing fabric and stuff that the supervisor trees do, one cool pattern is to put in a canary. So you can set up some routing rules that are like, okay, send just a teeny bit of traffic over here to this new build. And we're thinking of putting this new build up, but we don't know what it's going to do. And so we'll put it out there in the wild, taking on production traffic, because if you try and do fixtures and sort of a synthetic environment and load test, it's not the real world. So you want to take in the garbage in data that comes from the real exchange in a live environment. And if it dies, it doesn't matter because we let traffic fall on the floor, right? So canarying is a really cool way to assess these new operations and make sure that they don't cost too much in terms of time. Like if they aren't performing well, we're not going to do it. If they are, we'll finish a rolling deploy, and that build of that, the build will just roll out from there actually. So yeah, so this is kind of just an interesting thought, just on the trade-off between throwing machines at something or throwing people at it. Like almost every problem I've ever dealt with, you just throw more machines at it, like because like a couple more servers are way cheaper than people, right? And harder or easier to get. The servers are much easier to get than good talented engineers. This is one of those few places where you actually throw really good engineers at it. And optimizations can just save you tens of thousands of dollars when you have hundreds and hundreds of servers all doing the same thing. So we put a lot into tuning this and making sure it works right. And then, back to the workflow. If it takes too long, the supervisor kills it, and then to the outside world, it's just a 204, no content. Nothing happened. So we'll get into this slightly more, but like a big part of the strength of this, along with what we get for free with Akka framework, routing, those kinds of things, is we get to use off-heap memory for massive data stores like GeoIP. It's just huge. And then we are able to put the indices to those structures on heap, and it's just incredibly fast. I've had good combos, like talking to hackers in interviews and phone screens and stuff, and they're like, you totally could have wrote that in Node. And it's like, yes, but at a much smaller scale, this can work. But you end up starting to invent Akka pretty much on the one hand. And there's some things you just can't do. And we'll get into a few of those trade-offs in just a little bit. But something you might jump to is like, well, just put it all in Redis, right? But now that's an off-machine lookup, and that expense of a bunch of those versus an in-memory lookup is so significant that 30 millisecond timer, it's going to go off quite a bit. And you're going to have a very, very inefficient system that's like not doing the job a lot of the time. So that's core to what we're doing. All right. So before I move on to the next section, anybody want to question, comment, heckling?
So the question is, have you had those performance comparison between C and the setup? Are you behind on those? Do you lose many more like the guys in C?
Yeah, so the question was, have we done performance comparisons with C? Not for our total end-to-end product. We have with the easy stuff, but then those are degenerate tests. So you can test like very simple stuff like what's the performance of HTTP, and you test C and Nginx, and maybe some frameworks like Finagle. We did Golang. We did a bunch of tests just to test the base HTTP libraries and how they handle it. And like where we haven't gone that far is like to test it in full situation. Like how does it do with routing to workers? How did no because then we essentially have built it again in a whole other language. But our heart of hearts tells us, based on our friends and other people that do it in just C, it is a slightly better way to do it. And we end up with a footprint, a bigger footprint of machines because of our choice. But it's a conscious one at that. Yeah. Okie doke. Well, this is a Node meetup. And I'm glad nobody's left yet, that I can tell. Either that or you're being very polite to me. But, you know, we have there's 3/3 to our stack. The bitter stuff, that's what we talked about first. The Apache Spark stuff, which we'll talk about last, that's 2/3 of it right there. Node is really the other third, though. And we have this notion in our company of like everybody's full stack. And so, you know, we used to have a wall or a room in our old office where all the front enders go in there. And when you're ready, you like throw it over the wall, or you hand them a Jira ticket or whatever, and like the front enders do it, right? But we found that it was much better to join the backend API teams and front end into one thing. And we found that, like, just even in terms of like, if you want to look at it in a process execution example, it's like easier for any one worker to steal a task and just do it, rather than these artificial blockers that kind of make inefficient workflows. It's kind of like talking about concurrency and parallelism, which we have a few slides on in a minute. So for us, we use Node for our API. Actually, I'll just do the slide, why don't we? Yeah, we use it for our REST-based API. We have a lot of microservices. We have a lot of external integrations, companies like Nielsen, Alexa, SimilarWeb, a bunch more. Tag tester, automation, video encoding pipelines, and quality assurance type stuff. We have like Redis PubSub, UI notifications, system-wide messaging, all of this stuff. It's Redis and Node, and for us on the front, it's Angular. That's what that says. So, and actually, yeah, Selenium, Protractor, end-to-end stuff, that's all Node as well. So a big part of our use of Node is in our API layers. We pretty much dog-fooded this in the beginning by having a read-write API. I always chuckle because I never heard of the term read-write API. Aren't they all? Like, that's what they're supposed to do. But in our world, there was only a lot of read-only APIs from our competitors, and it's like they were just dropping off data for reporting, but you can never activate. So we made sure you could activate in our platform from day one, and with just a little kickoff meeting and some API docs and a sandbox and really good support, like we've actually gotten customers deeper into our system pretty quickly. It's awkward how short the meetings were. It's like they're in there, they have their own environment, isolated sandbox, and I always joke like this one, right? So it's like with Docker, we're spinning up stuff really quickly, and essentially everybody gets their own private video app API, because it's real dangerous, right? You're playing with fire here. It's like you're going to post stuff to our side automatically, and when you do, we're going to spend your money for you. So you want to have really good confidence that it does exactly what you want. So the necessity for a sandbox here, or a dev environment, if you will, that's your own, that has your own database and your own fixtures and all of this stuff, is really important. And then we even have a concept of like certain private URLs which can reset your database or wipe the fixture or load other ones. And you can even build specs and tests on top of it. Like people do some interesting things with their own private environment. I don't know about you folks, but I've written integrations far too many times on a dev server or integration server, which is shared. And so it's like super loaded down and it doesn't respond in time. It times out, or the database is all whacked or whatever. And it's like from stuff other people have been doing. So to have your own environment is really a powerful thing, actually. Another big thing that we've been into along the way is using Protractor and Angular for end-to-end testing, building happy paths, which is like common workflows through your application, all the main avenues of your UI. I always call it like a user experience contract. So it's like if these baseline set of tests work, it's not everything we do, but if most of the stuff is working, that's a good starting point. And in fact, when those fail, you fail fast and you don't run the full suite either. So very much into the front-end automation side of that. And when you're constrained, and pretty much that's the economics of everything that early stage companies have to deal with, is finite resources, products that are changing a lot, etc. This is a good place to focus your testing efforts because because you could go down a deep rabbit hole of writing tests everywhere and saving yourself from yourself. And I do agree with having all those things if you can. But what's great about end-to-end testing is they ultimately exercise all the other layers. And so by exercising the UI, you're calling out many other things, and you'll find problems in other layers beyond just the front end code when you do that. So there's a fun art and science to doing this, and not like hard coding magic values and building up test cases and fixtures and things that actually are done through the UI versus artificially. But that's actually a whole nother line of discussion. Something else we do with Node is tag testing. So since we spend other people's money as a business, they deliver their ad to us as a VAS tag. It's just an XML doc. And inside of that doc is like, different XML elements, and it calls out like what video encodings there are and what bit rates and formats, and some of them are good for your phone, some of them are good for a TV, etc. So there's all kinds of variants for the video files, and then you have like tracking beacons basically and some other kind of stuff. And so what happens is people will give those to us, and it will be a bogus tag, and it'll be their fault, but they'll blame us. So we have an automated environment which will load these ads in like test players and stuff, and then we use Node as an HTTP proxy. There's an observer where you observe everything going over the wire, and you can actually kind of parse out a VAS doc really easily and build an expected list of things that better go by on the wire or else this thing is broken. And you can see things like, hey, the link you've got there is HFFTP or whatever, // or it goes to a place that 500s or 404s, etc. We can look at the quality of what's inside of that tag and be like, yeah, we better not start spending money for you on this. And agencies and people will hand these tags all over the place, and they can get damaged in transit, kind of, And so, we inspect these tags for naughty behavior, and then we basically will short circuit wasting money on things that aren't going to traffic properly in the wild. I'll do a quick couple slides at the end. There's a cool plugin that I wrote back in September that does this in real time in your browser, actually. And then lastly, like UI notifications. This is our old GUI. Sorry, David. He thought that he would never need to see that again. Yeah, Alex.
With testing, I have a quick question. Do you guys use behavioral-driven development or test-driven development at all?
I'd say big fan of BDD, but no, we're more on the TDD side of things, actually. So such as like frameworks like Cucumber or whatever, where it's very, very expressive in the behavior. We're not at the BDD stage as a company right now.
TDD is pretty good though. So.
Absolutely. And yeah, so I'd say we've actually gone a little further away from the end-to-end stuff, and we're doing a lot more just straight test-driven development everywhere. But yeah, UI notifications are fun. And basically, it's a Redis pub sub, and from anywhere in our platform, you can emit a message to the pub sub and just send it off. As long as there's a UID in there, if David's logged in, then you'll get a pop-up message like, "Hey, yo, you're out of money," or this asynchronous long-running pipeline thing just finished, or whatever. And it's a cool way to give you a backclick to somewhere deep in the UI without having to give you 15 different steps in navigation. And so I'm a big fan of like flash messages or UI notifications. And actually, what you do is you build a activity feed out of this. So you kind of get a list of all the latest stuff that's happened. And it gives you kind of timely information if you're already logged in. And it eliminates a lot of these excess emails that you would otherwise have to send out. So if you're logged in and you get this message and you acknowledge it, it's not going to put you in the email queue. And that's a self-selective kind of feature you can do. Like you could say, no, send me the email anyways, or definitely don't. Like that's an experience I like to see. All right. So why didn't we use node.js for things? So I think that this is a relevant portion of the conversation. If you want to stop and get involved, just let me know and ask me a question. I think the nuances come out, especially in our problem area, but may not come out as much in others. So you may actually really effectively use Node for certain kinds of problems, but our particular one was not. So let's explore some of the strengths and weaknesses and the trade-offs between the languages and try and understand some key differences. Actually, I didn't plan to, but this looks like a good trivia question, actually. Does anybody want to jump in on this one? Yeah.
You want to know the difference between concurrency and parallelism?
Yes.
So parallelism is multiple threads, right? And concurrency is like an organization of things going on the same thread.
Pretty much, yeah. Yeah, exactly. So yep. Yeah, good. Let me get to a few slides, and that basically is what you said. So it's really commonly misunderstood, but it's worth diving into a bit. Concurrency does not necessarily mean in parallel. So concurrency is a way to build things, right? It's a way to express and compose things. It's about structure in your code, and it's about structure in the conceptual model. It's about dealing with a bunch of things at once, right? Parallelism is the simultaneous execution of doing a bunch of things, of multiple things at once, redoing things at once, right? And actually, there's a really good video on YouTube. There's many, but the Rob Pike video about this called That is really good. He gives a good example of like an OS running all kinds of devices, I/O, keyboard, screen, whatever, but only on one CPU. So it's a concurrent model. You can interact with it. You can click things. Things respond. But it doesn't necessarily have to be parallel execution. So the good example is like a single core running, like Windows 3.1, if anybody here remembers those days. So it's a sort of like preemptive multi-threading environment where there's still only one thing running at once. It's so darn fast you don't really know, you don't notice. But that's a concurrent model, but not parallel execution environment, right? And actually, for the people who are more visual, who knows what this is? Am I really that old? This is Tapper. Did anybody ever play Tapper? Yeah, okay. Right, so this is probably a good example of a concurrent environment because there's only one bartender, right? And there's all kinds of stuff that he's got to deal with. These things are they actually, I think they sanitized this and called it root beer tapper, but it's beer, right? It's Budweiser, and so you got to pull down on the knob. Literally, the game was a tap. When you played the game, you had to pull it down, I believe, and you had to service all these different people, and they get harder, and the people come in faster, and you got to pull down on the tap while the beer is filling up, and then you let it go, and then the person gets the beer, and it goes all the way out. But if you don't fill it up enough, they only go a little bit. So it's like the longer you stay here, the farther away the person gets. And these people keep rushing you, and they're thirsty, and they throw the glass back at you when they're done. That's what these are. And then if you don't get it in time, it falls on the ground, and then the round is over. All right, so this is probably a good, well, it'd be better if it was running and we watch the video or something of it, but this is a good example of a concurrent model because there's really only one thing doing the things, even though they're handling a lot of different scenarios all at once. And then just even one more example of that is this kind of thing. So here's your single core. It's doing stuff. It's doing multiple things. But really, while one thing's going on, the rest are like kind of parked, right? And by the way, this is kind of how Node works. Parallelism is more like this, right? And actually, you could overlay the prior example with this as well and be doing lots more things across two different cores. And it's kind of what your machine will kind of scale to whatever resources it has to kind of run things this way. Parallel is a lot more like this. There we go. Right, so that's doing a bunch of things at once. So, okay, yeah, I guess I have another trivia question here. I forgot about that. So can somebody explain Node's execution strategy in the context of that stuff? I'm going to go over here first.
Yeah, I remember when we talked about the JavaScript event loop.
Yes.
And so it breaks down its code into bite-sized little pieces that can run called kicks and sort of keeps track of them on a stack, and after each tick, it just goes to the stack and see what's next to be run.
Yes. In the context of those, actually here, in the context of these two things, is it
Definitely concurrency.
it's that, right?
Yeah.
I can kind of give it away, I guess. Right, exactly. Now, actually, has anybody ever worked with the multi-core libraries of Node? Yeah. So, I mean, then I'm wrong, right? Yeah, like the clustering stuff. Okay. So, I mean, with that, you can do a bunch of things at once, right? But there's some serious trade-offs with that, and that's what I want to talk about next. So, the single-threaded event loop is great for some and even most use cases, actually. And you can think of it as advancing as one small step at a time concurrently, right? But it does break single-thread event loop. It breaks down at some use cases, right? Like that, going back to that example, which was a massive geo IP database lookup. Many gigs of file, but stored in off-heap memory, but the index is on-heap. So it's kind of like really managing carefully, but not as good as you can see, the access to that stuff. You have one process per core, but if you launch it with the clustering stuff, you're going to have to copy the memory over and over again for every core. They're not going to share it. And when you start using services like Redis to do that, that's cool, but we have to operate at 30 milliseconds end to end. So also, and this has changed since I last did this. I did scale something maybe at like 50 or 80,000 requests per second with Node. And this is a long time ago, and we had to work really hard to do it. To message across cores, to build intermediary queues, to do counters, to do a whole bunch of stuff. And it just felt like we were building our own framework that was very one-off and very custom for our use case. We did it, but you know, you can drive with your feet, as they say too. So you know, that can also just move the characteristics to another place. So you could be doing all this work on all these cores and sending messages and message passing, and you can saturate the ability to pass those messages, or it could be that at the end of that whole process, a single threaded event loop is the thing that's processing it again. So you have to be very careful that these workflows don't narrow to some other place where you're just offloading the problem. So since in Node, in-memory is not practical across many cores, you have to sort of externalize those lookups, like I said earlier. Calling out to Redis wasn't an option for us on most stuff. It was in the earlier versions of our bidder, but we're like, oh, we can't do that anymore. So the more and more we realized that we couldn't just offload these requests, the less practical it got. So in-memory was the way to go. And actually, yeah, I mean, I was beating a dead horse there. I guess actually as a last point, one huge efficiency we get to, at least on top of Scala, and this is more the JVM than just Scala, that we get really efficient dependency injection. And so you can have a single handle on something like a Kafka producer or connection pool to something, and all of your different workers can tap into that, and you don't have to keep copying it for every single core. That's actually really efficient for certain operations, especially a lot of I/O, right? Stuff that's like more specific to the JVM, I think it's the fork join framework and the pool that's on top of it that we most benefit from. A lot of frameworks out there leverage this, not just Akka. The idea is that threads of execution can be forked off into smaller and smaller pieces, and then they signal back to the pool on their blocking intentions and where they're at and so forth. So that gives a lot of power to how the executor and how the scheduler is going to run. They can join back using signals, and they can use like work stealing algorithms to keep a machine with many cores busy all the time. And then using the signaling, the scheduler can kind of know when blocking is going to happen, or async processing, and actually a good adaptation is like certain data structures that are already built for concurrency, like concurrent collections. It's really hard to do this in other languages, actually. The data structures themselves are amenable to this kind of structure and scheduler. So in reality, they are already amenable to being processed parallel, basically, is what I'm saying, not just concurrently. So there are higher level abstractions for all that stuff. Futures, execution contexts, but there are some trade-offs too. So debugging these things can get really hard. The stacks can get all chopped up and fragmented into little pieces, and they do have tools to kind of reassemble this stuff, but it can be really tough actually. Yeah, so just going back to Scala, there's actually some interesting constructs too in the language, like you can wrap stuff in a blocking function. There's scala.concurrent and async.wait. Both of these things actually end up signaling back to the JVM and inform the scheduler about their intentions, so there's sort of a preemptive execution strategy that the lower level scheduler can employ. Frameworks like Finagle, it's like totally handled for you. You don't even know it's there. It just performs really well. And when we were doing a lot of that benchmarking, like we were talking about earlier, Finagle was definitely something we benched, and it worked exceptionally well, actually. And in fact, Golang was really good too. They have one of the best native HTTP libraries of any language. I have a lot of respect for Golang, actually. It handles HTTP really well. Okay, where are we at here? So yeah, I mean, Akka.io is something as part of we use in our whole cluster, and it's part of the effect of that that's really efficient is it's zero copy network stack. So it's not like moving stuff around in memory over and over again. It's like using very efficient algorithms to use zero copy in memory for stuff. Netty is another framework. Excuse me. A lot of this stuff is built on. There's plenty of frameworks that use Netty at a lower level, which is a similar deal where it's fast zero copy network and pipelining and so forth, and it's why a lot of really fast and efficient things use Netty under the hood. And actually, you can operate directly with futures and executors or execution contexts to kind of get a finer degree of control, of these signals that go to the lower level thread pool executors. So in Akka, the framework ultimately parallelizes the work because it's a concurrent framework. So you could like run an Akka app, or even just things in Scala, but you could run these things on a machine with 4 cores and it's going to run a certain way. You can run it on a machine with 32 cores and it's going to just be like, oh, cool, more things to parallelize across. Going back to that example where we did this in Node and kept scaling it more and more and more, we had to be aware of the hardware it was on and what the resources were. We had to like tweak and tune things with magic numbers and environment variables that changed, and it was very difficult to get it to really utilize things. This was a long time ago. Maybe there's good frameworks out there. I spent a while today looking for an Akka equivalent in Node, at least that did some of the semantics, and I found like POCs and stuff, but it doesn't look like they really even went that direction, quite honestly. And in my slide notes, I put up an interesting study that somebody did comparing Akka and Node for certain use cases, and it was actually Node won out in the low end of the concurrency spectrum. There's actually some overhead with Akka, but then it actually beat the pants off of it at a certain point. Actually, can I click it? No, sorry. Ask me later. Cool. So coming around the mountain here. How are we doing on time? We good? All right. So what's the other third of our stack? It's Spark. We use Apache Spark for a lot of stuff. We used it starting in June of 2014, and our entire stack is written with that. No Hadoop or MapReduce at all. Actually, some major news for us is we just did a PR that's going to be merged into Spark 2.1, and it makes Spark SQL work 10x faster in certain use cases. So Spark SQL is basically like using a SQL console like you would with MySQL or Postgres, but it's on like a multi-petabyte scale data warehouse. And so one of our best engineers wrote a patch that can do sort of like clustered indexing on chunks of files. And it's adaptive towards like, do you have 15,000 files for this query, or do you have just 6 or whatever? And so it does some really cool adaptive optimization towards Spark SQL. Spark's written in Scala. So if you're going to do anything with it, you're going to want to use Scala ideally rather than Python or Java. There's actually a few really idiosyncratic excuse me, things with scope in Scala where since you're working with a big cluster of machines and stuff, when things go out of scope, they can be garbage collected a little more efficiently and cleaned up. And the semantics to that are pretty much automatic versus having to go and explicitly do some of those things in other languages. Okay, so anyways, so I'm just going to go through a few of our use cases because I've already given you 2/3 of the stack. Let's just look at the last third. We do like streaming event ingestion. So earlier I told you about all these bid requests that are coming into our bidder, 100 zillion miles an hour, and so we take that and write it to Kafka. But after it goes there, it comes right back out with our streaming ingestion apps. So we'll take that, the events flow in, and then we buffer that in Kafka, and then we chunk it into files, and then they go into HDFS in our data warehouse. And when you chunk these things up, they're highly optimized for Spark SQL and querying them later, like an indexed columnar store. And another patch we did for Spark SQL about a year ago is we put metadata and boundary conditions so that while you're querying these things, you can kind of skip whole gigabyte or multi-gigabyte files like, oh, I don't need you, oh, I don't need you. And that data will get stored in a metastore. So it's like a very quick way to rule out lots of I/O when you're doing these queries and just let the query optimizer zero in on the exact files it needs because they'll already be really big anyways. So what's cool though is like nearly 2/3 of our entire company knows SQL. And when I tell that to people like on the phone, they think I'm talking about MongoDB, like no SQL or whatever. No, our people know SQL. So that's cool because we're still small and people want to do accounting functions or like troubleshooting and like why isn't this campaign winning or whatever. And so a lot of our customer service reps have basically learned it and they'll jump into the query console. My partner Ross does, right? You see him in there. We all cringe a little bit. Like just no delete or update statements. No, actually in a warehouse there is no delete or update. It's just read only actually. But so that's really cool. So it's cool to have petabytes of data accessible to everybody all the time. Here's another use case. Streaming event ingestion part 2. Events flow in from our ad server infrastructure, and these like inform things like pacing in our bidder. Like, well, how are we doing? Are these campaigns on track or not? And that informs the rates of bidding, maybe how we select which campaigns are up for BAT or whatever for fulfillment. And we do this rolling window join, which is a really cool thing. So, like, we've all done like joins in databases probably, or even like big outer joins. Those take forever. In fact, Redis is really, really good at large outer joins if you ever have that problem. But you kind of have to do this when you have petabytes of data a month. You're better off having a look-back window and doing a rolling window join on data as it's streaming in versus like going back in a month and outer joining or rejoining back on petabytes of data that may not even be resident anymore. So, for example, all these bid requests come in, but we don't win them all. So those aren't really as much of a concern for us except for forecasting and stuff. But the ones where we win, we need to know what the original state was on that request. So with a rolling window join, we'll go back in a short amount of time in a quicker lookup fashion. Usually the window is minutes or hours or a day. Right now I think we're in the hours range. But we can take the original data relevant to a later event, smash them together, and then put it into the warehouse. Now you don't ever need to join it again. It's essentially denormalized at the point of the situation. And that's huge. So when you go back and query it later, you're also not writing really complex SQL. It uses a SQL interface in like ANSI or Hive SQL format, but it uses dotted notation too. So it's basically like JSON. It's kind of like the mixture of Mongo and some RDBMS. So you don't have to keep joining a bunch of tables and that kind of funky business. You just need to know the dotted notation and the things you want to get to in the JSON structure for each record. So that's huge. And darn it, it's supposed to play while I was talking. And so anyways, yeah, that prevents the massive joins down the road. There we go. Yeah. So that's your streaming window join right there. Another cool thing we built is this cluster manager called Flint. We're open sourcing it next year. Basically, it allows us to run lots of Spark clusters on the fly. We plug it into Jupyter, which is like a notebooking thing or a REPL. And you can mix in SQL and Scala and all these things. You can plot stuff. And it's a way we all just get in there and play around with data. This is the Easter egg version of the GUI, which I did with emojis and shit. But like we actually have material design version coming, right? Yeah. That's partly why we can't open source it, incidentally, because you shouldn't have to click a coffin, close down the server or whatever, or the baby chick, whatever. So what's cool about it though is we do regularly spin up clusters with 800 cores, 5 terabytes of RAM, and throw these huge jobs at it, right? So I'll explain a few of those workloads really quick. We'll be open sourcing it next year. So earlier I was talking about cross-device graphs and that thing. That's just a huge tensor, basically. And on top of that, we have billions of signals of data and our cross-device graph, and we run this job every so often, which pushes Spark pretty much to its limits. And so we'll spin up a huge ad hoc cluster, and we'll do that. Right now we do it on on-demand instances in Amazon, but we're working to make this launch on spot instances, which can be way cheaper. It could be like 5 to 10% of the cost of an on-demand. And then basically, it's like it literally didn't become economical and practical for us to do this as often as we do without just being like, okay, give me a crap ton of machines right now, right? Okay. There you go. Billions of signals, 150 million unique users, and a single ID in our platform, which relates to all the devices that are in orbit around a person in 3 space or whatever that is. Okay, so the other thing we do is we know who watches what on TV, so we get signals on TV consumption data. That's in the hundreds of billions of signals. It's quite a bit of data, and so we've built the industry's best multi-dimensional TV consumption map, and I'll show you a few pictures of that in a minute. So we're able to build like TV buying plans. It sort of handicaps the price, figure out the best geographies, day parts, and the TV shows which are best for our customer to buy, given their objectives and stuff. So this has taken Spark to its limits as well, because we were crashing Spark trying to process this with an arbitrary amount of compute. And certainly chunking it right and breaking it down is all part of making that work right, but it took our team to its limit to be able to process that amount of data. And spinning up clusters on the fly made it possible. So here's a few use cases. This is kind of fun when we were playing around with the data. I'm not going to ask you if you know what this is because you just no way of knowing. But actually, these are zip codes or DMAs. I think they're DMAs. No, zip codes. Yeah, they're zip codes. So let me see here. The people who watch Bravo are red. And the people who watch country music television are blue, and the purples are kind of like a mixture of both. And actually, this is way better when you zoom way in. Actually, it's a little bit over sound. It's almost too hard to see. But what you'll find is that there's a lot more country music television watchers in like in here, right? And there's a lot more Bravo along the coasts. And it's kind of a mishmash over here, and that's also just representative of where people live too. So you kind of have to get the actual things that are standing out, you need to normalize it against like population density and some other things. So
it's a little bit like political maps.
Yeah, yes. I have a couple others that you guys might like to. So yeah, that's a good one. And we have another version of this. Is it like a topo.json D3 thing or something? Which has the districts, the political districts, by the way. So we do have a map for that, but I don't have a grab of it. This one's good. This is Judge Judy versus Jeopardy watchers. Okay, so Judge Judy is the black, and Jeopardy is the bright red, and unfortunately, it gets a little muddled, but like the dark red is a mixture of both. So as you get into really populated areas, people watch both. So what you're going to see, I guess, in this kind of visualization is just outliers more than anything else. Like, let me see here. What was black again? Judge Judy. Yeah. So a lot of Judge Judy here, not a lot of Jeopardy, etc. Right. So you can. The visualization of this is not as important as the actual end product, which is like building a plan to figure out where you should run things. So you could either be figuring out where to buy television or video on demand or OTT or whatever. Or maybe you already got a buying plan and you want to reverse that into a way to target people digitally, like on their phones. And you can certainly geo-target in these types of pockets and stuff too. So the indexing goes both ways, and that's a big important distinction there. And don't worry, I only have a few more slides. All right, so last but not least, this is a hack project I mentioned just a little bit ago. It's plain old JavaScript, but it's ES6. So this is a vast inspection tool. This is actually kind of fun in that it's like actually what the XML looks like, because right, XML makes trees really easily. But as an ad's being requested, it's like you have an MP4 file, and these are Flash FLVs, and you have the option, actually how Chrome is disabling Flash now. Does anybody notice that? Up in the upper right, you have to click to play Flash now. So the ad is delivered in two variants, JavaScript and Flash. And in this particular case, my player wanted to play the FLV version. But it can also run through this JavaScript version, and instead, new things would get parented under that as an ad is playing and as beacons are firing and all that stuff. And up above, under impressions, that's what is like considered a user sync. So people they redirect, set a cookie, redirect to somebody else, and this stuff just happens all day long. And if you were to go in your net panel or your Chrome inspector for your network, it would just be a sea of stuff, and you're like, what is all that stuff? And you have no idea. Well, when you trap the XML file and parse it out, you can build a map of the things that you want to look at and visualize it in a much cleaner way. And this is just a visualizer for network traffic, but rolled up against the protocol used for serving ads. And up top, those are actually beacons that fire as you're watching it. So there's always a start pixel. That's how we know we ran and won. And then there's these quartiles that show you how far through the video ad that somebody's loaded. And they make these interesting chains. It was written in ES6. I think I pretty much told you all this. So basically filtering through a sea of activity that would otherwise be really hard to look at. And so, yeah, I mean, originally it was built out of the need to do discrepancy checking. We were like wondering why one of our partners just wasn't adding up. We're like, they say that they're running on CNN. Let's just go look at CNN a bunch of times. We reload and reload and reload and reload, and they're never coming up. So we're wondering what's going on. And so rather than just digging through the net panel all day, like till our eyes go googly, I decided to whip this up over a weekend or two. And so, but actually it evolved in some interesting things. I think now we've had to go through all the use cases of how to attribute, like, well, this thing brought in this thing. And it's kind of like imagine a bunch of JavaScripts that can keep including each other. That's kind of a fun, hard problem to attribute because you have to basically use ASTs or some other kind of thing to reverse all the code that brings in code that brings in code. But it's the same with like XML and even Swift files. So we had to do a lot to actually build the attribution methodology for this, even decompiling Swifts and extracting symbols, and it's pretty crazy stuff underneath the hood on that. Yeah, all right. There we go. So, I guess that's it for my prezzo. I wanted to loop back and kind of turn it over to everybody else here. Who's got statements, questions, heckling?
Can we clap?
Not yet, no. So, let's see. Can we turn up the lights at least? Yeah, there we go. All right, well, sorry. Yeah. We got some questions.
Fascinated by the technology. I'm trying to put this in
Kind
context, that's all.
Kind of, yeah. So think of it like this. You can see video ads on the page in a lot of different ways. Let's talk about the most legitimate ones. You go to YouTube. They pre-roll a 5-second skippable video.
Okay.
And you're like, skip, boom.
Oh, gotcha.
That's a video ad.
Okay. Yeah, I hate those things.
You're on Hulu. Yes, I was going to say you can blame us for all of this. But in a way, right, like the content owners need a way to pay for these expensive video streams and to be influenced to be encouraged to make new content, etc. But there's also illegitimate video ads in our opinion too. Like how many people have been to a site where it's like, what's that sound? What's playing? What? And it's like, and then they're scrolling and there's like this thing. Actually, South Park did a brilliant episode about this like a year or so ago, where it's just like the web, even the experiences on the web are just way worse than they were in the early web because you're just bombarded everywhere. There's so much fraud wrapped up in that. There's videos playing that you can't see. And in fact, in our industry, viewability has become like the major metric. And part of what we've learned to do is optimize at the front end and the bid stream side and be like, just don't even show us stuff that's not going to be considered viewable by our industry. and we got it up to like a 95 percentile efficiency, and we've done white papers and all that good stuff. But yeah, so and then there's in-banner stuff, which is kind of like slightly less icky, but it's like they take they take a display ad unit like 300 by 250, and then they cram a video in there. So video that plays in places that it kind of shouldn't. We're also not that interested in that. We're focusing on all the premium experiences. And if you, yeah, so, and it just lastly, like if you look at where consumption's going, like a lot of people are cord cutters. My house, my kids don't even remember what it's like to fire up a cable box. YouTube, Hulu, Netflix, a bunch of video sites I don't even know about. Like that's where it is at. So all that consumption is going over to what's considered like OTT, Apple TV, all these specialized devices. Build your own. So, yeah. There was another one. That's a great question. So, good question. Up until lately, we've hovered around 20 to maybe 24 engineers and data scientists. I did a mea culpa sort of blog post a couple weeks ago about how we over-applied our process early on. We were very strict, Scrum and Agile, and we took most of all that out. And so we wound up with something very flat, very few meetings, very end-to-end, at least at this stage of our company. But we've spent some time over the last month figuring out how to grow out of that and how to pod and do special forces and cross-functional teams and full stackers, which are people who understand the front end and Node, and they're learning Scala. That's another major thing we do is we cross-train people in Scala. So basically, we're getting into a place where we're having about 4 teams, and they're going to all have their own roadmaps and their own things, just because we're growing too much on too many fronts, and just the sheer management aspect of end-to-end, we've outgrown it, basically. So we're going to gamify it. I've seen other companies do it too, where you have a team name, and every sprint review once a month is kind of a competition, and actually Lyft used to do this. You have a trophy that has bling on it and stuff, and like every new winner they add a little more bling, and they put that on their pod desk, and like there's actually really cool ways to make it fun. But, yeah, I did personally, yeah. But actually, we have some very dedicated Scala engineers. They're like, why didn't you use Scala.js? But apparently, it's a really good gateway into learning and using Scala because it's a Scala-esque Scala, but on the JavaScript runtime. I'd say actually it boils down to talent, though. Like the accessibility of talent is a lot easier with Node, and I wouldn't say with Angular. I'd say with React and Redux, there's a ton of talent out there. But we started building our platform a long time ago on Angular, and we've redone it a couple times. And it's just we can't scrap the whole thing and restart it yet. But we'll do another build next summer. We have. Moving petabytes of data around is tough, but that wasn't the whole blocker. We spent 6 months building a game plan to move off, and we still have this like in our playbook. We will do it. When it came down to executing it, it would have been in our most critical money-earning quarter of Q4 this year. So double footprint, double infrastructure, lots of risk, etc. So we're going to. A lot of companies like us run on bare metal in dedicated data centers. We've had the opportunity to go on the same switches with some of our exchanges, like right on the switch. So sub-millisecond access times. I don't even know if you can get sub-millisecond, but 1 millisecond access time, etc. But also, as you do this, you have a lot of connective tissue you need to do, and you need to do direct connects and pay for bandwidth, and you kind of need to do that anyways. But it's a Herculean effort, and we know we need to do it. And when you get into the level of volume where the capex makes sense, you can actually that's how you really justify it. So we're getting there. Yeah, and early on, we played around with composing all kinds of different services in different languages for this. So we wrote our original bidder was actually Python. And it was really just because we had a lot of good Python developers around that also had some level of experience in this space. And so we wrote front-end routers in Finagle, Golang, and Node. And that's what we were benchmarking actually, to build like in-memory filters for just dropping stuff. Like at the time we built blacklists and any reason we could find to drop that traffic, like we do it in the front end. And you could do this very easily with a lot of languages basically. And then the next step was like, well, wait a minute, we don't want to necessarily drop that traffic. It's still got to go into Kafka, it's still got to go into our warehouse because we want to still forecast against it. And then there's a slippery slope of like, well, wait a minute, this language doesn't do well with the Kafka producer libraries. And this language does good, but and so as we started composing more services at the front, like certain things fell out of the running pretty much. But again, Golang was actually really, really good at this. I got it up to about 19,000 requests per second on one box. It was like a C3 8XL, and it basically won. I didn't write a native C app, but we probably could have. Actually, Nginx is really fast too with this. Yeah. Well, it's hard for them to get a seat on the exchange. So it's not, all they're going to do is use just one of 2 or 3 other competitors that do what we do. Certainly the data means a lot. And I guess our biggest selling point right now is what I mentioned earlier, which is 95% on target for viewability. So a lot of agencies are like, just run it. Like they don't care to go in and do the extra little whatever. Like they just ask us to run it and make sure that the KPIs are right. So it's a bit of managed service on the one hand, like just run it. And then there's a bit of using our UI, which is like, I want to come in and tool on the knobs. I want to come in every day and optimize a little more. And then the third use case is just people using APIs. They're like, I don't even want to log into your UI except for occasionally to do the last mile optimizations that our engineers didn't program against or whatever. So it's a mixture of those 3 things: managed, self-serve, and API. All right, yes?
Did you ever try
Last, okay, this is going to be the last question.
Did you ever try Elixir for any of those?
We did not. We don't have, that's Ruby, right? Is that?
It runs on Erlang. It's just
It runs on the Erlang VM, but yeah, no, we didn't get involved with that. We were already working with Scala by that point. I've heard some cool things from developers about it. All right, well, I guess that's it. Thank you very much.